Hello, this is Teksim, and this is the quiz for the explanation of chapter 9, 10, and 11. So, the table of content today would be first, we're going to start out with chapter 9, the center of gravity and centroid. And then we're going to talk about chapter 10, the moments of inertia, and the last one is chapter 11, which is called the virtual world. So, without further ado, let us start with chapter 9, the center of gravity and centroid. The center of gravity, and first of all, it's the center of gravity, the center of mass, and the center of a body. Center of gravity is a body that is composed of an infinite number of particles in differential size. And so if the body is located within a gravitational field, then each of these particles will have a weight, which is dW. These weights will form a parallel force system, and resultant of the system is the total weight of the body, which passes through a single point called the center of gravity. As you can see, I have shown in a picture below, which is a center of gravity of our human bodies located at our belly button. So we can find the center of gravity using the formula x bar is equal to the integral like that, but what we have to take a look here is dw. So it's the weight of, it's the differential of the weight. So note that x bar, y bar, and z bar are the coordinates of the center of gravity, and the x which has the curve, and y with the curve, and z with the curves are the coordinates of the arbitrary particle in the body. So the center of mass, which is the next point of a body, is the point at the whole mass of the body appears to be concentrated. Generally, the center of mass lies inside the body, but the position may change. Center of mass depends on the shape and its mass distribution for a continuous distributed object. So to find the center of mass, we need to manipulate the previous equation. Instead of the derivative of the weight, it can be written in terms of the derivative of times mass times gravity, and since g is constant, which is g is equal to 9.81, it would cancel out, making the whole formula into something like it's shown down below. Notice the difference. This time it's the derivative of mass, dm, and previous it was dw, the derivative of weight. So moving on is the centroid of a volume. It says that if a body is made up of a homogeneous substance, one type of substance, then its density or rho will be constant. Therefore, a differential element of volume dV has a mass of dm is equal to r times dV. And if we substitute these elements into the equation, into the previous equation, to find the center of mass and cancelling out, or we would obtain the new formula of the centroid C, or the geometric center of the body, which is the same as the previous one, but this time it's dV, the derivative of volume. That's the only difference. So moving on to the centroid of an area. It says that if an area lies in the xy plane and is bounded by the curve y is equal to fx, then its centroid will be in this plane and can be determined from the integral using the formula from down below. So these integrals can be evaluated by performing a single integration if we use a rectangular strip for the different short area element, as you can see in the picture. If we use a vertical strip is used, the area of the element dA is equal to y dx, and its centroid is located at x is equal to x, and y with the curve is equal to y divided by 2. And if we consider a horizontal strip, then dA is equal to x dy, and its centroid is located at x with the curve is equal to x over 2, and y with the curve is equal to y. So staying with the concept of centroid, but this time it's we're talking about with the line. So the centroid of a line. If a line segment or a rod lies within the xy plane and it can be described by a thin curve with y is equal to f of x, then its centroid is determined from it's the same formula, but it's the definite integral from L to a specific point, and L is the segment of the line, or the line segment. So the differential element is related to the Pythagorean theorem, which can be expressed as dl is equal to dx squared plus dy squared, and we take the square root of everything and progress further with the equation. We get dl is equal to the square root of 1 plus dx over dy over dx squared dx, or can also be dx over dy squared and then dy on the outside. So procedure for the analysis. For the differential element, first we select an appropriate coordinate systems. For the line, it's represented by the line segment dl. For the area, it's the rectangle dA. For the volume, it can be the circular disc dV, meaning both area and volume have a finite length, radius, and a differential width, differential elements. The next one is the size and moment arms, and they are expressed by length dl and area dA and the volume dV of the element in terms of the coordinates describing the curve, and express the moment arm xyz, the centroid and the center of gravity of the element in terms of the coordinates describing the curve. Integration, which is simple enough. We substitute in all the elements and express the functions, and we solve for the integral, and we find the region, which is the area under the curve. So moving on to our next point, which is the composite body. So a composite body consists of a series of connected simpler shaped bodies, which may be rectangular, triangle, or semicircle. So such a body can be often be divided into many sections, and if the weight and the locations of the centroid can be found, we can sum the whole thing together to find the centroid of the center of gravity of the whole body. So we imagine the body with consists of particle, so that the resultant weight WR is equal to the sigma of W, and we can rewrite it into x bar times WR as the equation shown below, so that we can shift it to the other side, and then we find that x bar, y bar, and z bar does not relate to the integral. So respectively, we can use a sigma in that sense to find x bar, y bar, and z bar. So for the procedure of analysis, for the composite part, we should use a sketch, divide the body and the object into a finite numbers of composite parts that are easier for us to understand. The composite parts can be a geometrical shape that are simple to find the center of gravity. Then we subtract the other parts to get the normal, to get the original parts back. For the moment arm, we should establish the coordinate axis on the sketch and determine the coordinates of the centroid. And for the summation, after we find all the x, y, and z respectively, using a sigma on each segment of the body, we can then plus the whole thing together like the equation shown earlier, this one, to find x bar, y bar, and z bar by just summing them up together and divide by the whole weight. So let us look at an example. It says to locate the centroid of the shape down below. So the composite part, the plate is divided into 3 segments. Three small rectangle number 3 is considered to be negative, so it must subtract from the larger 2, 1 and 2. And for the moment arm, the centroid of each segment is located as indicated in the figure as shown below. And by this summation, we should write the segment 1, 2, and 3, and this should include the area, x with a curve, y with a curve, and a curve times x and the other one. And for that, we can find the whole thing, and with the summation of it, x bar is equal to the negative of 0.48, and y bar is the it's equal to 1.22 feet. So let us move on to chapter 10, which is the moment of inertia. So the definition of moment of inertia for areas. The moment of inertia for an area is defined as the second moment because it derives from the formula that involves with integral. Consider you have an object that is replaced underwater, which has a pressure P. The pressure is different. That is different depend on the depth, which can be written as P is equal to gamma times y, where gamma is the specific weight of the fluid. Thus, the force acting on the differential area, dA, of the plate, dF, is equal to P dA, and substituting it in is equal to gamma y dA. The moment of this force about the x-axis is therefore dm is equal to y df, and would be gamma would equal to gamma y squared dA. And so integrating the whole area of the plate would give us m is equal to gamma the integral of y squared dA, and the integral of y squared dA is sometimes referred to the second moment. So the moment of inertia by the other definition is the differential area dA about x and y axis, are the differential d ix is equal to y squared dA and d iy is equal to x squared dA. For the entire area A, the moments of inertia are determined by the integration ix is equal to the integral from A of y squared dA, or iy is equal to the integral from A x squared dA. As you can see below, these are various shapes and the formula that is derived from using the concept above. And as you can see, for circle and the rectangle and the half circle all have different formula for the inertia. So moving on is the parallel axis theorem for an area. The parallel axis theorem can be used to find the moment of inertia of an area about any axis that is parallel to an axis passing through the centroid and about which the moment of inertia is known. To develop this theorem, we will consider finding the moment of inertia of the shaded area down below. To start, we choose a differential element, dA, located at any arbitrary distance y from the centroid x-axis. If the distance between the parallel x and x-axis is dy, then the moment of inertia of dA about x is dix is equal to y prime plus dy and the whole thing square and times dA for the entire area. So therefore we get ix, which is equal to taking the product of y prime plus dy square, we get the integral of a y prime square plus 2 dy y prime plus dy square and times dA. So the first integral represents the moment of inertia of the area about the centroid axis I bar x. The second integral is 0 since the x prime axis passes through the area centroid C, so that the integral of y prime dA is equal to the y bar prime of the integral dA is equal to 0 since y is equal to 0. Since the third represents the total area A, the final result is therefore is Ix is equal to I bar x prime plus a dy square. And similarly, Iy is equal to I bar y prime plus a dx square. For the polar moment of inertia, we can write it as J of O is equal to Jc plus a d square. So the form of these three equations states that the moment of inertia for an area about an axis is equal to its moment about a parallel axis passing through the area centroid plus the product of the area and the square of the perpendicular distance between the axes. Moving on to the next concept is the radius of gyration of an area. The radius of gyration of an area about an axis has unit of length and is a quantity that is often used for the design of column in structural mechanics. Provided the areas and moment of inertia are known, the radii of gyrations are determined by the formula kx is the square root of ix divided by a, or ky is equal to the square root of iy divided by a, and k of o is equal to the square root of j of o divided by a. So the radius of gyration, or the gyradius of a body about the axis of rotation, is defined as the radial distance to the point which would have a moment of inertia the same as the body's actual distribution of mass. If the total mass of the body were concentrated there, mathematically the radius of gyration is the root mean squared distance of the object's path from either its center of mass or a given axis, depending on the relevant application. So, procedure for analysis. In most cases, a single integration can be used to determine the moment of inertia. This can be accomplished in two ways as shown in the procedure below. So first we should choose a rectangular differential element with a finite length and width. If the curve defining the area's boundary is expressed as y is equal to f of x, the element should be placed in such a way that it intersects the curve at any point x and y. So for the case 1, orients the element so that its length is parallel to the axis about which the moment of inertia is computed. This situation occurs when the rectangular element is used to determine Ix for the area. Here, the entire element is at a distance y from the x-axis since it has a thickness of dy. Thus, Ix is equal to the integral of y squared dA. And to find Iy, this element lies the same distance x from the y-axis so that Iy is equal to the reverse, which is the integral of x squared dA. For the second case, the length of the element can be oriented perpendicular to the axis about which the moment of inertia is computed. However, Ix is equal to the integral from a y squared dA, and the other one do not apply since all the points on the element will not lie at the same point at the same moment arm distance from the axis. It will be necessary to calculate the moment of inertia of the element about an axis parallel to y-axis and passes through the element centroid, and then determine the moment of inertia of the element about y-axis using the parallel axis theorem. Moving on to the next point, which is the moment of inertia for a composite body. So a composite area consists of a series of connected simpler parts of shape similar to the other one, such as rectangles, triangles, and circles. Provided the moment of inertia of these parts is shown can be determined about the common axis, then the moment of inertia for the composite areas about this axis equals to the algebraic sum of the moment of inertia of its part. So procedure of analysis. First, we divide the whole thing into many composite parts which are easier to understand. And if the centroid axis for each part does not coincide with the reference axis, then we should use the parallel axis theorem. For the summation, the moment of inertia of the entire body is determined by summing the whole result together, including the composite part. If it has the empty region, it is used to subtract instead of summing or plus. Moving on to our next point, which is the mass moment of inertia. The mass moment of inertia of a body is a measure of the body's resistance to angular acceleration, since it is used in dynamics to study rotational moment. Consider the rigid body shown below as we define the mass moment of inertia of the body about z-axis as I is equal to the integral from m or squared dm. Here, r is the perpendicular distance from x to the arbitrary element dm. Since the formulation involves r, the value of I is unique for each axis about which is computed. The axis which is generally chosen, however, passes through the body's mass center G. If the body consists of material having a density ρ, then dm is equal to ρ dv. Substituting, then we find the new formula for I, which is the integral from v or square ρ dv. And since ρ is constant, we can push it out to make I is equal to ρ, the integral from v all square dv. So the procedure for analysis. If a body is symmetrical with respect to an axis, then its mass moment of inertia about the axis can be determined by using the single integration. The shell element. If the shell element having height, radius, and thickness, then it can be found by dv is equal to 2 pi y times z and dy. This element can be used in I is equal to ρ, the integral of from v all square dv. For determining the moment of inertia iz of the body about the z-axis, since the entire element, due to its thinness, lies at the same perpendicular distance or is equal to y from the z-axis. Disk element. If a disk element having a radius and a thickness of dz and the volume is dv, then dv is equal to 2 pi y times z and times y. In this case, the element is finite in the radial direction, and we can the formula that we used earlier cannot determine iz. Instead, we should perform integration using this element. It is first necessary determine the moment of inertia of the element about the z-axis and then integrate this result. Moving on is the Mohr circle. The Mohr circle is a graphical representation of the transformation equations for plane stress problems. It is useful for visualizing the relationship between normal and shear stresses acting on a stress element at any desired orientation. The picture below is an example of a Mohr circle. So this is the stress transformation formula, as you can see, which include taus and sigma, and the derivations of the Mohr circle. So it says that if we vary theta from 0 degree to 360 degree, we will get the possible value of sigma x1 and tau x1 y1 for a given stress state. Eliminate theta by squaring both sides of 1 and 2 together. The equation would adding up the two equations together, we find the equation as shown below. Moving on to chapter 11, which is the virtual work. So the definition of the virtual work. The principle of virtual work was proposed by the Swiss mathematician Jean Bernoulli in the 18th century. It provides an alternative method for solving problems involving the equilibrium of a particle, a rigid body, or a system of connected rigid bodies. So work of a force. A force does work when it undergoes a displacement in the directions of its line of action. Consider the force F in the picture that undergoes a differential displacement dr. If theta is the angle between the force and the displacement, then the component of F in the direction of the displacement is F cosine of theta. And so the work produced by F can be found using the formula du is equal to F dr times the cosine of theta. Notice that the expression is also the product of F and the component of the displacement in the direction dr times cosine of theta. If we use the definition of the dot product, we can say that du is equal to F dr. Work of a couple moment. So the rotation of a couple moment also produces work. Consider the rigid body below, which acted upon by the couple forces F and the negative of F that produce a couple moment m having a magnitude m is equal to Fr. When the body undergoes the differential displacement shown in below, respectively, the couple forces do not work during the translation dr times a because each force undergoes the same amount of displacement in opposite direction, thus cancelling out the work. During rotation, however, F is displaced by dr prime is equal to F dr. So it does work. du is equal to F dr prime is equal to Fr times d theta. And since m is equal to Fr, the work of the couple moment m, therefore du is equal to m d theta. Virtual work. The definition of the work of a force and a couple have been presented in terms of actual movement expressed by differential displacement having magnitudes of dr and du. Consider now an imaginary or virtual movement of a body in static equilibrium, which indicates a displacement or rotation that is assumed and does not actually exist. These moments are first order differential quantities and will be denoted by the symbol the small data r and small data u. The virtual work done by a force having a virtual displacement delta r is equal to delta u is equal to f times cosine of theta times delta r. Similarly, applying the same delta, we can say delta u is equal to m delta theta. Moving on to our final topic, which is the principle of virtual work. It states that if a body is in equilibrium, then the algebraic sum of the virtual work done and the couple moment acting on the body for any virtual displacement of the body would result in the delta of u is equal to 0. So a virtual displacement is imaginary. For example, it does not really happen. It has a differential displacement that is given in the positive directions of a position coordinate. The principle of virtual work is generally used to determine the equilibrium configuration for a system of multiple connected members. Forces or couple moment that do not virtually displace do not do no virtual work. So that is it for my explanation of chapter 9, 10 and 11. And if you have any questions, feel free to drop it down below in the stream. And thank you very much.